Okay.
I was also wanting to do
We're
that.
live, but I gotta do something first, so hang in there.
This day, I want to do it, just so you know.
Okay, get a desk and take it out home. One of you can go in the science workroom, the other two can face opposite from one another. Get your calculators. I have a CC 40, so you don't need to have one of those. Calculator pencil.
Oh, yeah.
You're welcome to write on the back of these if you want to show your work on something, or you can grab a scratch paper, whatever.
Wait, go in the science.
Somebody needs to go in the science workroom. The other two can stay in the hall. Okay, here you go. Bring her back. Okay.
You know why?
Are we gonna have to take this last class when we're done with school?
I am so screwed for the chapter 5 class.
There you go, we're lucky.
Like, cause we get done over before school is out, so we're gonna have to.
Okay, here we go. Did you bring a note? Good, because I'm already live. I punched the button too soon, and so I can't go to the attendance right now. Okay, on section 6 or chapter 6, you'll notice the title of it. Last one we're doing, by the way. Applications of trigonometry. For a little while, we are going to spend our time on concept of vectors.
Oh.
And this one, 6.1, section 6.1 is called vectors in the plane. As you know, I like the author's chapter overview and things, kind of lets us know where we've been, where we're headed. So at the top of page 502, if you want to get there with me and read with me, then this is what it says. We introduce vectors in the plane, perform vector operations, and use vectors to represent quantities such as force and velocity. So it's kind of about physics once we get that nuts and bolts together. Physics relies a lot on vectors. Vector methods are used extensively in physics, engineering, and applied mathematics. Vectors are used to plan airplane flight paths. The trig form of a complex number is used to obtain the log's theorem, which will be at the end of the chapter, and for finding the nth rows of complex numbers, meaning numbers involving I. Parametric equations, they're talking about the entire chapter here. Parametric equations are studied and used to simulate motion. Pretty important way of doing it too. If you ever take physics of any kind, maybe even chemistry, you're going to need to know these kinds of things. One of the principal applications of parametric equations is the analysis of motion through space. Not space like out up beyond our atmosphere. It means like from me to Mr. Cobb. That can be space too. Okay? Polar coordinates. Another of Newton's inventions, although James Bernoulli usually gets the credit because he built it first, are used to represent points in the coordinate plane. What else? Good planetary motion is best described using polar coordinates. We convert rectangular coordinates to polar coordinates and pull it back to rectangular and study graphs of polar equations. That's the one thing we're going to do, study graphs of polar equations. The rest of it is required. So, tells you kind of where we're headed. And we're going to start with vectors in the plane. And I kind of like his introduction to that too. He says it's better than, well, I don't know about better than me, but he makes it more complete, make sure I don't forget something. So let's read that real quick and then we'll get going on the map. It says some quantities, like temperature, distance, height, area, volume, can all be represented by a single number that indicates magnitude or size. Other quantities such as force, velocity, and acceleration, displacement, they don't include that in there, but they should have magnitude and direction. Since the number of possible directions for an object moving in a plane is infinite, you might be surprised to learn that two numbers are all we need to represent both the magnitude of an object's velocity and its direction of motion. We simply look at ordered pairs of real numbers in a new way. While the pair, parenthesis, a comma b parenthesis, determines a point in the plane, it also determines a directed line segment or arrow with its tail, the beginning point, at the origin and its head at the point AB. The length of this arrow represents magnitude, while the direction in which it points represents direction. Because in the context of the ordered pair AB, with parentheses, represents a mathematical object with both magnitude and direction, we call it the position vector of AB. We'll see what this all means in a few minutes. And denote it as, and for lack of a better word, rather than parentheses, we're going to call that symbol hat. Hat, A comma B hat. When you have little pointy things that gather that same point together that are pointy instead of parentheses, you are talking about the end point of that vector, whose tail is at the origin. So, while this, what I'm saying is while this is the point 3, 4, this is the vector 3, 4. Because we added a thing that goes from, that's supposed to be straight. I had to freehand it, but it's supposed to be straight. Starts at the origin and goes to the point 3, 4. This is called its head. This is called its tail. And this is how we graph it. And when we put little hats around it instead, we mean the vector that extends from the origin to that point. Okay? The length of the vector is the magnitude. Like, for example, if you had 30 miles an hour vector compared to a 60 mile an hour vector, the 60 mile one would be twice as long. They might be headed in the same direction or different directions. And there's lots and lots of times when we want to talk about vectors, or we get vectors given to us, information given to us where the tail is not at 0, 0, somewhere else. So I want to talk about how you handle that next. It's really easy. It really is. Okay, so let's take a look at the top of page 503. They give you a definition. Everything's highlighted. It's all there. And by the way, I don't know did I just mention this? Did I tell you that when we write this like this, that we call this component form? That's component form. There's other ways to write vectors. For example, you'll see this in a few minutes, but just to show you there's an opposition to this. This is called the component form of a vector. There's also, we call it unit vector form. I just call it IJ form, would be this. That is also the same vector. We'll talk about why that is in a few minutes. But that's called IJ form. You got component form up there. I prefer component form. Most people do. But this is an extremely valuable form. And by that way, that does not mean imaginary number. It means a vector in the horizontal direction. And it means a vector in the vertical direction. That's I and J, horizontal and vertical. Don't get confused. That's not an imaginary number. But this is an extremely valuable thing if you're going to study electronics at all. And you're going to send beams or wires full of electrons in certain directions. You get vectors is very, very important. Okay. I want you to look on page 503 in sort of the middle of the page in that left column where you see two vectors plotted in the plane. See that? All that's required is that there be a length of it, which is magnitude, and it's got to be headed off in a certain direction. Then you've got a vector. And this particular vector goes from -4, 2 to -1, 6. -4, 2 to -1, 6. So our vector has its tail here and its head out here. We can't really give that a component form of the vector. You might say, well, yeah, this is -1, 6, but that the component form only applies if its tail's at the origin. I'm going to write these numbers in here so you can see them clearly. I hope you can. It's -4, 2, and this one is -1, 6. These are the points anyway. I'm not going to put hats on those because this isn't a vector. It's just the beginning and the end point, the tail and the head. So I want to ask you, if I were to take that very vector, very, very same vector that has the same length and heads off in exactly the same direction, I need you to know that if I had another vector like that, they would be equivalent. They're not equal because they don't occupy the same space. But we would say that they are equivalent to one another because they're the same length, have the same magnitude, and they're headed in the same direction. That makes them equivalent, okay? So since that vector does not have its tail at the origin, if I did have a vector whose tail was at the origin, headed in the same direction with the same length, that would be a much, much easier thing to work with. So my question is, if I were to pick this thing up off the page and lay it down here, what would be its endpoint? Because that would be its component form. So the question is, I guess, how far down do I have to move it so that we're in line to scoot it over here? How far down have I got to come? 2. And how far over have I got to go? 4. So if I came down here 2 and over 4 with the head, that should give me an equivalent vector. They look like they're the same length and headed in the same direction. And now that they got the tail at the origin, I've got this component form of the vector is 3, 4.
Okay, like 3 parallel.
They have to be that parallel means they're going in the same direction. They have to be the same length, meaning they have the same magnitude. These are equivalent vectors, and it doesn't matter where you put on the grid. It doesn't matter where you put a vector as long as it's headed in the proper direction with proper length. And so it's always most convenient to put its tail at the origin if you can and work with it from there because it's the same vector. You know what I'm saying? It's not the same place, but that doesn't matter. That isn't what makes it a vector that's equivalent. It's got to be headed in the same direction. It's got to have the same length, and both of these do. But this is a more convenient one because we can write its component form, including only 1 point instead of 2, and have to work with that. Question is, how could you use these numbers for the original one, tail and head, to get to this one without having to draw it and count it all the time? Because sometimes these are not convenient, nice whole numbers that are small. We need to be able to take any vector and move it so that its tail's at the origin and its head can be called in component form. How do you use these numbers to get these numbers?
You just go at x2 minus x1 and y2 minus 1.
Try that, see what happens. If we took x2, this one right here, and subtracted x1, what would we get?
Or add.
Oh, yeah,
Do you want to add or subtract?
I like.
I don't. How do I get a 3 out of -1 and -4?
-1 minus -4.
-1 minus -4 will give you 3, right? Is that just coincident, or is that true for 6 and 2? Does it matter if we go -1 minus -4, or if we go -4 minus -1? Would that matter? It does, because this minus this is -3, and that's not where we want to be. You know what I'm saying? So to get these two numbers, which are the component form by shoving the tail over here, what you do is we had to go down to, I don't know if you can see the reconciliation between these numbers and going down to and over 4, but you take the x's, you take the head x minus the tail x, and you take the head y minus the tail y, will give you the y form on the component. And that's called the HMT method, head minus tail. HMT method, head minus tail. X minus x, y minus y, gives you a new point. But what it'll do is it'll shove this into the corner here with the origin, and it will give us the endpoint in component form. So this one and this one written as 2 points, and this one written just in component form are equivalent, and this is far easier to work with. You'll see in a few minutes. So that's how you convert it. So look at example 1 with me on page 503. We've got 2 vectors that are not in standard position, we call it. They're neither one in standard position, but we want to prove that they are equivalent. The direction might be kind of hard to prove. Well, no, it won't be. It won't be. Remember you said they have to be parallel? Okay. Parallel means same slopes. Okay. So if I wanted to prove they were equivalent in length, what I could do is take the upper left one, the one that's in the second quadrant, and I could take -1 minus -4, which would be 3, and 6 minus 2 is 4. So I know this one in component form would be the component 3, would have component 3, 4, right? If I did that with the other one, I'd have 5 minus 2, which is 3, and 3 minus -1, which is 4. And that one has component form 3, 4. I don't really have to find the slopes, because if both of them in component form land right here, they're equivalent. I don't have to find the slope. Are you with me? Hey, moving along. So this isn't very hard so far. Pretty easy arithmetic. Once you understand what you need to do, the arithmetic is easy. Now, I told you that these things in component form have their tail here, but still, a vector has magnitude and direction. We haven't talked about either one of those. All we've talked about is how to plot it on a grid, and that is to plot the point that is represented by this hat thing, this component form. Plot that point, connect it with the origin. That's it. We've not talked about how long it is. which is its magnitude, or which direction it's heading, which is the angle made with the x-axis, hence the trig. Okay? So we talked about either one of its pieces. That's what we're going to do next. So think about this. To find the length of this vector, can you see that it is a really quick application of Pythagorean theorem? And not only that, one of the legs is 3 and the other one's 4.
5.
What? Yeah, it's going to be 5. I thought you meant one of the legs was 5, and we go. Oh. Okay. Yes, the length is 5 because 9 plus 16 is 25. Whose square root is 5? Okay. There's a reason why we're using 3, 4 to study this. So the arithmetic is very hard. You can focus on the concepts. But what I want you to notice is that the horizontal component, we call it, because that's how far out you have to go, is 3, and the vertical component is 4, because it's in the x and y position, which we've studied all through this trimester. It's these two guys that you will square, add, and square root to get the length. No matter what this is, if you can get that tail tucked into the origin, then all you got to do is square this, add them, and square root, because that is Pythagorean theorem every time. The component form are the lengths of the lengths. Okay, so they have a way of writing this. We're talking about, I think we're talking about a velocity vector. You'll notice just up above, I don't want to do this stuff in the blue box at the top, by the way. I want you to look at the discussion just before the green box on page 504. It says, if you handle exploration 1, which we didn't do, so I want you to go to the next paragraph. It says, the magnitude of a vector v is also called the absolute value of v. So we're using v for vector, and it's called the absolute value. We'll discuss that a little bit later, too, why that's called that. So it is usually denoted this way. So if we want to know the length of it, we use v for vector, just to talk about it, and this we will call the length of it. In some books, they will use this to distinguish it from, it looks like absolute value, but it's got train tracks on both sides instead of just a single line. And that means we're talking about a vector here, but we're still talking about the length. In this book, they just go ahead and use the absolute value. We're not talking about the absolute value of a number. We're talking about the length of a vector. That's what this means, this symbol. And it is going to be equal to the square root of a squared plus b squared. I don't need those. If vector v is this. Does that make sense, all this new notation? If you don't have a vector in standard position and you want to find its length by not moving it to standard position first, which I always do. I always just move to standard position. I do the head minus tail, get myself 2 numbers, and then square and add those. But you could instead write that vector's length, this particular one, doesn't correspond to this, but this particular vector over here, if it's written in this form, you could, of course, write it like this. Because you're doing the head minus tail as you square it and add it. Okay? You all right with that? So you could go to the length directly if you wanted to. It's exactly the same since they're equivalent vectors. It's exactly the same as doing this, doing the head minus tail and then doing this. Okay. All right. That's pretty easy stuff. Moving on. Vector operations. Now we're going to talk about adding and subtracting vectors. We're going to talk about multiplying vectors in the next section. And we will know vectors. They just don't work out. It's not that division isn't possible. It's just that we will multiply by the thing we want to divide by is reciprocal. It's all multiplication. Okay. All right. So there's an interesting picture in the middle of page 505. And you might think that if you had 2 vectors that you wanted to add together, that you would just take their lengths and add them up. The reason why you can't do that is because when you're adding 2 vectors, they don't always head in the same direction. As a matter of fact, very rarely. So if you will look on page 505, you have in the middle of the page there, you got 2 blue vectors, u and v, and the red one that connects them after you hook them up that way is u plus v, and that's a new vector whose name is u plus v, and they're showing you 2 ways geometrically, 2 ways to find it. You can take u and tuck his tail into the corner, and then take V's vector and move it up so that its tail is on U's head and stretch it out in the direction it's going to go. And then you connect the original with the very end tail. And you can do that with several vectors. It doesn't have to be just 2. geometrically speaking, you could also let both vectors have their tails be at the origin and stretch them out the way to go. See how V is equivalent to the V in the previous picture? V, which was up top there, is now got its tail at the origin, but it's still going in the same direction, same length. Okay, so both their tails are tucked into the origin. And if you create a parallelogram by the top dotted line there is equivalent to vector V, and the right side dotted line is equivalent to vector U, again, tail. Then if you stretch it from the, or something stretch it from the origin to the other corner of that parallelogram, then you've also got vector U plus V. So one's called the parallelogram method, and the other one's called tail to tip or tip to tail method. Both will get you the same vector U plus V. But it's not just the length of U plus the length of V, because the red one would be longer if that were the case. Right? Are you still with me, Sarah? Okay. You were looking down really hard, and I was thinking, oh, she's asleep.
No, I was just looking at it.
Okay. I just wondered. Okay. So, and I'm just going to give you the nuts and bolts of this. To add two vectors together, you add the x to the x and the y to the y, and you now have component form for a result. The resultant is the red one. We call that the resultant rather than, you can call it u plus v, but it's the result of adding u and v. It's a resultant vector. So take a look at example 3. And it says, let's see if we can do all of this. I haven't talked to you about scalar ones either. If I wanted to make this one twice as long, I would multiply by 2 and I would have 6/8. And 6/8 would be right here, and that would be twice as long. And so when you want to if you multiply by 2, it just doubles the magnitude. If you want to multiply by half, it cuts the magnitude in half. At least it's pointing in the same direction. Okay. So with that in mind, look at example 3, and it says we've got u equals -1, 3. And they've got it in component form, which means we can assume that u's tail is at the origin. That's u. And we have v, which is 4, 7. I don't know that they use equal signs. They may just put it really close to it like you would a point to, I don't know. What did I say it was?
4, 7.
And we want to do these 3 things to these. It's not hard. It really isn't hard. Pretty quick and easy. We want to do u plus v, 3u. And what else?
2u plus -1 of v.
Plus -1?
So, yeah, 2u
Like this?
plus -1.
V.
Like this?
Close the parentheses.
No, -1.
So -1 and close parentheses v.
Okay. Like this?
The parentheses is on the -1, but yeah, sorry.
Plus parentheses.
Like,
Forget
-1 times v. What this really means is 2u minus v. That's what that means, just like you might expect. Okay? So if you understood what I said before, adding things together, u plus v is just going to be the vector, and I expect you'll be able to do this arithmetic in your head. U plus v is going to be 3, 10. Y'all clear? Pretty easy. Okay. 3u is going to be -3, 9. And u minus v, or sorry, 2u minus v is what this really is. 2u would be -2 minus 4 and 6 minus 7. All the harder that is. The arithmetic's easy, especially if the numbers are small and whole. Even if they're negative, it's no big deal. Okay. Look at example 4 with me, please. This can get kind of rough. This one right here is where we hit a little rut in the road. We're going to have to slow down a little bit for this one until you understand it. What we have here is what's called a unit vector in the direction of something, v or something else. So let me just talk to you about that. I'm going to keep the numbers positive. It could go in any direction. You can still deal with it, but I don't want to throw in the negative numbers yet. If I've got a vector out here, let's say 7, 5. And each one of these, if I was going to measure this with a ruler, each mark on the ruler would be as long as one of these boxes. Okay? So obviously, this vector is more than 1 unit long, right? And we could tell exactly how many of these units it is long by taking 49 plus 25 and square rooting, right? Obviously more than 1. Well, what we want to do is figure out the component form of a vector, a unit vector. Do they use U for it? Find a unit vector. They don't have a name for it. We're just gonna in the direction of V, and V has this for a component form, which is 7,5. What I mean by a unit vector, I mean in a vector that is only one of these units long, one of these little baby units long, headed in the same direction. So that means that the numbers that go in here are going to be pretty small. But here's the idea behind it. If I were to lock these off like this and come down here ways like this, so that now I can't just come out one and go up, because you can see that point right there if I've even drawn it freehand right. It's not doesn't connect this corner right here. And so the length of that is going to be, I don't know. But I do know this, that I want the length of it to be 1 vector long. I think it's going to be about right there. We'll pretend that's that right, okay? Right there is 1 vector long, and that would form a triangle that looks like this. And that little baby triangle right there is similar to this one, because its hypotenuse just headed off in the same direction, right? Now, what was the length of this one? It was the square root of 49 plus 25 square root of 74. Okay, so the length of this was the square root of 74. I want the length of this to be 1. So how much am I going to have to cut this back to make this 1? I'm going to have to divide it by the square root of 74, right? Then I'm going to have to divide this by the square root of 74 and this by the square root of 74 to back it off to these right here. Because whatever I divide this by to get a 1, I have to divide these by the same thing, because the triangles are similar to make them proportional. You see what I'm saying? Yeah. So while this was 7, this little piece of this triangle down here is going to be 7 over the square root of 74. Ugly, but that's got to be its length. And this one right here has got to be 5 over the square root of 74. And this component form of that vector is out this much and up this much, so its component form is this. The component form of that, the component form of the unit vector for this is 7 over the square root of 74, comma 5 over the square root of 74. Because I had to cut the hypotenuse down by root 74, I've got to cut the sides down by root 74. And it is the sides that make up the component form. This is the horizontal side, this is the vertical side. Does that make good sense? So what we've come up with here, using just those numbers, is if I have a vector like this, V is equivalent to AB, then the unit vector in that same direction is going to be V, the vector V, divided by the magnitude of V. Yeah? Which is equal to, if you want a bunch of stuff here, but I think you'll understand this, which is equal to A divided by the square root of A squared plus B squared, comma, B divided by the square root of A squared plus B squared. You follow all that? And you might think, why are we even doing this? Unit vectors are extremely useful. You just have to trust me on that. They're very, very useful things, and it's important you be able to find them so that they're only 1 unit long, then you won't have to deal with the square root of 74 in the hypotenuse. The hypotenuse is 1. Remember how we did all that unit circle stuff, and we forced you to learn that the cosine of 60 degrees was 1/2, but the sine was root 3 over 2? Instead of eliminating the halves and just letting the thing be 2 units long, we made you do it with 1 unit. It's important that we be able to do unit things. All right. If you look at the left of, let's take a look at example 4. They've got the vector -3, 2, and it says find a unit vector in that direction. and verify that it has a length of 1, that actual vector, take a look at what they do here. I'm not gonna go through the whole thing, but to find the length of vector v, it would be 9 plus 4, which is the square root of 13. And so you would take -3 over negative, look at what they've got down there a little ways, -3 over root 13 and 2 over root 13 is the component form there. And then they say verify that it's 1 unit long. Well, you find the length of that vector using Pythagorean theorem. You get 9 over 13 plus 4 over 13, which is 13 over 13, which is 1. Okay, so they did it on a different vector, and this one had a negative in it, but it didn't seem to cause any trouble. Right? It was in the second quadrant, but it's okay. Next thing is this IJ form, because a unit vector leads right into this, sort of. Sort of does. This IJ form of a vector, you've learned component form, and they're really, really easy to go from one to the other. One has a plus sign in it, and the other one has little hats around it. All it means is this, now that you've learned to multiply by scalars and add vectors together, it says if you've got a vector headed out like this, I don't know where it is. Anyway, if this is a unit here, I'm gonna put some units on here. I don't know where that thing actually landed. Maybe I'll redraw it. I don't know. But if you've got one going out in this direction, what you can do is take this vector, which is the unit vector in the horizontal direction, and this vector, which is the going in the vertical direction, and we can just call this vector, since it's a unit vector, instead of using A and B, I'm going to use I. This has a length, well, this is just the I vector, it's horizontal. This is the J vector, which means that this vector out here, this vector out here is going to be, let's say that landed right at 1, 2, 3, 4. This was 4, and this is 3. This will be, no, not component form, sorry, will be 4 of these plus 3 of these. Because remember what we said, if you take to get this vector right here, you would add a vector. I don't know if I'm making much sense. I'm not doing a very good job here. If I go out 4, if I take this vector that's going out like this, and this vector that's going up like this, and that's what I've got there. This is 3 long, this is 4 long. Then if I come out here and draw this dotted line out to there, and this one up to here, that this would be the sum of those two. That's why this is a sum. This vector is 4 times the I vector. This vector is 3 times the J vector. And so this vector is 4I plus 3J, because writing them together. So that's called the IJ form. It is a sum of what we call unit vectors in the horizontal and vertical direction. These are unit vectors down here, and we would multiply them by a scalar to get them to go out a ways and up a ways. But when we add those two vertical and horizontal components together, we get this slanty one. And so this has a sum. This has a plus sign in it. It's exactly the same as this in component form. They're the equivalent. One's got a plus sign. One's got a comma and hats. They're the same. Okay. All right. So you may have to work with either one of those forms, but it's not a big deal. If I am ever presented with a couple of vectors in this form, I immediately convert them to this. I'm good at these. This one takes me a second, though not much. It's just a little harder because this is not familiar to me. This is very familiar. That's all. This is the only thing I ever learned when I was in high school. So I just convert it real quick and then deal with it in the form. Okay. Now we got to talk about directions. We've talked about how to find out how long they are, how to cut them back to a single unit vector, how to write them in different ways, the length of it, but we've not talked about the angle. The angle's really easy, as you might suspect, because if we know a lot about the lengths, we can use inverse tangent to find the angle. Okay, take a look at example 5, and let's see if we can reconcile this based on what we know. It's easy stuff. You just haven't done it in quite this way before, so I'll show you. Okay, let's take a look here. And this is our task. It says in example 3, find the components of the vector v whose direction angle is 115 and its magnitude or length is 6. So we all know that 115 degrees is in the second quadrant, but not very far into it. So this is 6, and we need to find the component form of that vector. You okay on that? So make a triangle like you've been taught to do all trimester long. If that is 6 and this is 115, what is this? What?
65.
65? Not a familiar angle. That's okay. It's not a familiar angle. But what we need to do to find this component form is find this length and make it a negative because we're going left, and find this length, make it a positive because we're going up. Cosine of 65 is equal to x over 6. Sine of 65 is equal to y over 6. And x, if I solve both of those, I get 6 cosine 65 6 sine 65. Here's what's even better. If we did this, we would have to, and it's fine to do this. I do this every single time, but I remember when I write it down to make this negative. I think that's the safest way, in my opinion, to use the concepts of everything and use this reference angle as a smaller angle down here and get these. If you wanted to do this, it would give you the appropriate signs on both of them automatically. The reason I don't like this method, going this route, rather than assigning the signs myself, is because this doesn't belong to a triangle. So I have to remember, I'm talking about this, but I really mean this, because if I do this, it will give the appropriate signs. I don't like to do that. What I like to do is use that reference angle, and it'll always be between 0 and 90. That's just me. And then make sure that I attach the appropriate signs. Okay? So what this comes down to, if you've seen the way we put this together in this triangle, what it comes down to is assigning the right signs on this, but it's always the length of the magnitude of the vector times the cosine to give you the first component, right? And the length of the vector times the sine to give you the second component, which we've always known. This is cosine sine. And so the magnitude just gives you the proper length. You have to take the magnitude times the cosine and the sine. Like I said, I like to use these between 0 and 90, make sure I give it the appropriate sign. So I would do this. I'd grab my calculator, make sure I'm in degree mode. When we deal with vectors, we're usually in degree mode. So grab your calculator, and I do the cosine, or 6 cosine 65. And we get 2.54. It's negative, and 6 sine.
We need to excuse the tennis players at this time. Those tennis players that are traveling today are excused.
5.44. That's what I got. Is that what you got?
Yeah.
So again, make sure that you take time to attach the appropriate signs if you're going to use the reference angle like I do. You don't have to. You can use the 115 and it will give you the signs correctly, but that means you're trusting your calculator a lot because the 115 doesn't belong to a triangle, so you're wondering if that's really right. So not, I do. Okay, moving along. So that's how we find direction angle. Let's do example 5 right quick, and then we'll be done with 6.1a. Example 6 says there's 2 problems, and it says find the magnitude and direction angle of each vector. Find the magnitude and direction angle. Oh, we haven't gone after actually finding an angle. We were given an angle here and a magnitude. Here they want to give us the component form. So now we're going to get where it is, where the head is, and we've got to find its length and
Angle.
angle. Thank you. Thank you. Okay, so this first vector is 3, 2. 3, 2 is about right there. This is 3, this is 2. So this is 3, 2. We have to do 2 things. We have to find its magnitude and its angle. I would suggest a triangle again. Magnitude's going to be square root of 13. Direction angle is going to be, if you know that this is 3 and 2, this angle right here is going to be the inverse tangent of 2/3. Does that make sense? Because the tangent of theta is 2/3, so theta, the angle, I'll call this theta. Theta is going to be the tangent inverse of 2/3. And since we're in degrees, do that. Inverse tangent, whoops, inverse, come on. Inverse tangent of 2 divided by 3. 33.69 degrees. I think they let you round to the nearest 10. Yeah. Okay. Look at the B part, -2, -5. But now we're in the third quadrant. -2, -5's down here ways. So this is 2, -2. This is -5. This is the vector, magnitude, and direction. Again, for me personally, I recommend that. Right angle is there. This is 2. This is 5. Makes the magnitude square root of 29. Yeah, a little bit more than 5. Square root of 29. Theta would be this right there, that alpha right there, inverse tangent of 5/2. Are you okay on that? Okay, and that's alpha. So what's the inverse tangent of 5/2? .2 or 68.20. Which means that theta is what? This being theta. .248, right? That's its direction angle. So again, I always use the right triangle, find out information, and then reconcile it with what I need to if it's an angle greater than 90. This theta turned out to be alpha because we were in the first quadrant. Alpha here turned out to be 68, so theta turned out to be 180 more than that. You okay? Pretty easy, right? Especially since all the other stuff that you've got underlined, you already learned. Okay? We'll learn applications tomorrow. This is just practicing all these funny little arithmetic skills that you learned that's kind of strange today. None of it's very hard. People get through it pretty quickly. Okay? Do not forget, you have a test to study for, which will be given on Monday, ready or not.